In this video, we're going to learn about convex mirrors. We'll see how to draw ray diagrams for convex mirrors, and then we'll also see applications of convex mirrors. Before seeing this video, you should watch the lesson on concave mirrors and also on plane mirrors to understand how to do the ray diagrams for those. As a reminder, there are two main types of mirrors we're studying in this course. We're studying the plane mirrors, and we're also studying the curved mirrors. Curved mirrors can be concave, that curve inwards, or they can be convex, which curve outwards. In this video, we'll focus on the convex mirrors specifically, the ones that curve outwards. Before we go into ray diagram drawing, we're going to take a look at some of the important terminology you need to know to be successful in this lesson. Just like concave mirrors, convex mirrors are cut from a sphere, like a ball. If you cut it and take that segment out, there's an inside portion that curves inwards, but then the outside part curves outwards, and that's a convex surface. Convex mirrors, that's their name by shape. They curve outwards. By what they do to light, they're called diverging. And so if you look at these parallel rays that are parallel to the principal axis and to each other, when they hit the convex mirrors, the light rays move away from each other instead of going towards each other. So that's why they're called diverging. So it's opposite of converging. Similar to the concave mirrors, there are some terms you need to know regarding convex mirrors. There is a principal axis which cuts the mirror in half. The vertex is still the middle portion of the mirror, so right over here. The focal point is interesting. So if you look at these rays that are parallel to the principal axis, when they hit the mirror, they do diverge. But if you draw your tracebacks, you'll see that the tracebacks meet at a focal point behind the mirror. So the focal point is, we would say, virtual or behind the mirror. So it's where the traceback rays of the reflected rays of parallel light rays meet behind the mirror. That's your focal point. And then just like there was a center curvature, well, there's also a center curvature behind the mirror that's 2 times the distance of the focal length. So focal length would be this distance here from mirror to focal point, and then radius of curvature would be from mirror to center curvature. But that center curvature to the mirror is always twice the distance from the mirror to the focal point. So if this is 5, then this is 10. So again, very similar terminology to what we saw in the concave mirror, the main difference being that the focal point is a virtual focal point where the virtual rays or the traceback rays appear to meet up. And so you can see that in both these images here. Just like we did for plane and concave mirrors, we'll describe images formed by convex mirrors using lost or salt. And the interesting thing about convex mirrors is the characteristics are always very similar, regardless of where you place the object. So in concave mirrors, if the object was placed at C, beyond C, between C and F, at F, or between F and the mirror, you had different image characteristics. For convex mirrors, you can see the image characteristics are all very similar. So if you look at image number 1, or object number 1 here, its image is over here. You'll see it's smaller and upright and a bit closer to the mirror. If you look at object number 2, its image is over here. Again, smaller than 2, still upright, closer to the mirror than 2. If you look at object number 3, the image is here. Smaller than 3, upright, closer to the mirror than object 3. So as you can see, location is always DI is less than DO, so the image is closer to the mirror than the object. Orientation, it's always upright. The size of the image is always smaller than the object, so it's smaller. The type, now you can see it's behind the mirror, and you can see it's made by traceback rays all the time, the image. So that means that the images are always virtual. So the characteristics are always the same. There is a bit of a trend. You might notice that as you go from 1 to 7, object 1 to object 7, you get closer and closer to the mirror. So as the object gets closer, so does the image. And you'll also notice that as the object gets closer, well, the size gets bigger. But it's still, the image is still always smaller than its corresponding object. So there are still trends. Here you can see an application before we go into the details. This is a security mirror in a store, and so they're put up in the corners, and because they make everything small and upright, you can fit the entire store basically in this mirror because it's a lot smaller now. And so someone who's looking in the mirror can see anyone in the store, what they're doing behind the shelving here in case they're stealing. So that's one practical application of these convex mirrors. Just like with concave mirrors, there are some rays that you can memorize to avoid having to use a protractor. So these are the main rays here. You can have a ray parallel to the principal axis. It reflects as if it's coming out of the focal point behind the mirror. So you have to make sure you line your ruler up here, make your reflected ray, and make your dotted lines so that the trace back goes through the focal point. And make sure you put your arrows, of course. That's one of the rays. The other ray is one that goes towards the focal point, as if it's going towards the focal point here on this side. But it doesn't hit because there's a mirror in the way. When it does hit the mirror, it reflects parallel to the principal axis, and then you would trace back for that reflected ray over here. Other rays you can do are the one that heads towards the center of curvature on the other side, but doesn't go on the other side because there's a mirror in the way. So it bounces back on itself, but the trace back goes through the center of curvature, because as you know, that's the normal. Another ray you could do is one that goes to the vertex. You measure the angle of incidence, that's your angle of reflection as well, and then you draw it on this side, but this requires a protractor. So personally, I would use 1 and 2 and maybe 3 if you need it, but really just 2 rays per point as per the convex mirrors. So similar to concave mirrors. So please make sure you memorize these rays, and that will help you when it comes to drawing the ray diagrams. So we'll do a practice problem together. So all the steps are listed here. Here you have an object, so a pencil. It doesn't really matter where you are relative to the focal point in a convex mirror. There's always an image that forms, even if you are at the focal point on this side. So let's say the focal point here is 5, and you have a distance of 5 here. You might think, oh, there's no image if you're there. No, that's not true. That's only true for concave mirrors. So we do a ray parallel to the principal axis. That ray reflects as if it's coming out of the focal point behind the mirror. And then you draw the trace back so it goes through the focal point. Then you can do a ray that goes towards the focal point here, but it doesn't hit because there's a mirror in the way. But you line it so that your ruler would have gone through there if you did. And then you make your reflected ray parallel to the principal axis. The rays won't cross on this side because they diverge. But you draw your trace back ray of your reflected ray, and here, where those trace back rays meet, that's where your image is going to be. And you can see it's upright because that was the tip of the pencil here. Base stays on the principal axis. You can see it's smaller. You can see it's closer to the mirror. You can see it's virtual as well. So let's try this out one more time. Parallel to the principal axis, as if it's reflecting or coming from the focal point. So draw your trace back through that focal point there. Draw it towards the focal point, but again it stops because there's a mirror in the way. Make it parallel for the reflected ray and make your trace back for that reflected ray, and where these trace backs meet, that's where your image is going to be. Upright, virtual, closer to the mirror, and smaller than the actual pencil, the actual object. And that's the case for convex mirrors. There's no other scenario for it. It's simply smaller and closer and virtual and upright. Remember those rays? The trick is not to get confused between convex rays and concave rays. So you do need to make sure you get those rays straight in your head. Understand when to use the concave rules. They're very similar, but almost reversed in a sense. But it's the same idea. It's just it depends where your focal point is. So for concave, if you were parallel, you'd go through the focal point. Your focal point would be on this side. But if you're convex, when you're parallel, you still kind of go through the focal point, but it's your trace back ray that goes through the focal point. So remember, convex is the virtual version of it. Here's another practice problem. You can try this out and see if you're on the right track. So again, a ray. So pause the video first, try it out yourself, then check your answer. A ray parallel to the principal axis, reflect it as if it's coming out of the focal point. Draw your trace back so it goes through the focal point. A ray that goes towards the focal point but doesn't hit the focal point because there's a mirror in the way, so it reflects parallel to the principal axis. Make your trace back ray, and here is where your image would form. Smaller, closer, virtual, and upright. You can try this one out as well. Pause the video, try it yourself. So if you're checking your work now, parallel to the principal axis, reflect as if it's coming out of the focal point, draw your trace back so it goes to the focal point. Then do your next ray, which is towards the focal point, but it hits a mirror, so it reflects parallel to the principal axis. Draw your trace back, and then we have our image right there, upright, virtual, smaller, and closer to the mirror. So those were all examples for ray diagrams for convex mirrors, much simpler in terms of less scenarios than concave mirrors, but you do still have to make sure you don't confuse your plane, concave, and convex. As usual, we have applications you should know for this type of mirrors. So for convex mirrors, these are your main applications. You should be able to not only state the application, but explain why the convex mirror makes sense for that application. So for example, when I look at the security store mirror, well, it's great to have a convex mirror because, first of all, everything is upright, so I know what I'm looking at. Everything is smaller, so it can fit, the whole store can fit in the mirror. And those are the two main reasons why it would be neat. It would be a good idea to use the convex mirror. Everything is also a bit closer because DI is less than DO, so you can get a better view of what you're looking at within the store. Here we have rear view mirrors, side view mirrors, and you can see this little statement here. It says objects in the mirror are closer than they appear. But side view mirrors, the reason they're convex is because they allow you to see more of what's behind you when you're driving. If you've ever gone to an ATM to withdraw money, they have these little security mirrors here that are convex, so you can see more of what's behind you for security purposes. Over here, this is someone at the border checking under the car to see if there's anything hidden under there. There's a convex mirror that makes everything smaller and fit into the mirror, so you can see the whole underside of the car without having to kind of bend down. You can get a better view of all the different corners in there as well. And again, that's all because of the characteristics that the convex mirror provides. So part of your experiential learning that I'd like you to do is just examine yourself in a spoon. Take a look at a spoon, both sides, and answer these questions. Is it concave or convex? Explain. How do you know which side is concave and convex based on the image characteristics? Describe what the image would look like in a concave side and in a convex side. Take a minute to just explore and see if you can tell that and explain it to somebody around you, the two mirrors, curved mirrors within the spoon. You should summarize your this lesson within your lab notebook according to teacher instructions for your lab notebooks. Make sure that if you need any extra support, you watch other summary videos here, complete any learning goals and practice problems assigned by your teacher as well.